In the last weeks of 2020, Jupiter and Saturn will appear very close together in the sky. They will appear closest on December 21st, when they will come within 1/10 of a degree of one another. That's just a fifth of the diameter of the Moon. Even though they will appear close from our point of view, in reality the two giant planets will still be pretty far apart. Jupiter and Saturn orbit the Sun on near-circular orbits at distances of roughly 5 and 9.5 astronomical units respectively. In such a configuration, the closest approach between the two planets is about 4.5 astronomical units, or 4.5 times the distance between the Sun and the Earth. It wasn't always like that, however.
Like dinosaurs, Saturn and Jupiter roamed. They sculpted this system that humans call home. Their orbits first shrank, then shifted and grew. Our Earth was constructed from rocks they plowed through. And later on, there was a big instability. This time, the giants expressed their hostility. The ice giants' orbits were strongly affected. An extra one may have been fully ejected. The Earth was bombarded, no planet protected. We don't have a time machine, can't see the past, but models can answer some questions we've asked. To test our ideas, we use simulations on giant computers with huge calculations.
When our Sun was born, a little over 4.5 billion years ago, it was surrounded by a massive dense cloud of gas and fine dust. The planets of the solar system all formed from the raw materials present in this solar nebula. The cores of the giant planets formed first, within a couple of million years at most, and this allowed them to capture and hold on to their massive hydrogen and helium-dominated atmospheres until today. Closer to the young Sun, in the hotter inner solar system, progress was slower. Here, rocky planetesimals, planetary building blocks about the size of a large asteroid, took longer to form. Gravitational attraction and perturbations by the outer planets allowed these planetesimals to grow. This N-body computer simulation shows how moon-sized building blocks, the small dots, moved around and grew in the presence of a fully formed Jupiter, the black circle, over the course of a few 100 million years. The system that forms in this particular realization resembles Venus, Earth and Mars, and even has a small asteroid belt located between Mars and Jupiter. By studying the orbits and physical properties of the planets, as well as those of the comets, asteroids and Kuiper belt objects, astronomers and planetary scientists try to piece together more and more information about this messy initial planetary formation phase. Two theories that have been put forward and developed recently and prominently feature both Jupiter and Saturn are the Nice model, named after the city in southern France where it was developed, and the Grand Tack model, named after the sailing manoeuvre. The Nice model addresses the period just after the accretion of the giant planets was completed. It argues that the solar system's 4 outer planets, Jupiter, Saturn, Uranus and Neptune, were formed in a more compact configuration, surrounded by a swarm of smaller, asteroid or comet-sized bodies. This computer simulation shows how the orbits of the outer planets, shown as circles, interacted with the leftover planetesimals, shown as green dots. Over hundreds of millions of years, the combined effect of many small gravitational interactions with these planetesimals resulted in the planets themselves slowly moving outwards. This led to an instability and final orbits for the planets that were considerably further from the Sun. Such a scenario does an excellent job of explaining the current orbit of Pluto and other objects in the Kuiper belt region located beyond Neptune's orbit. Some versions of this scenario start with 5 giant planets, one of which ends up being ejected from the solar system, never to be seen again. One of the consequences of this outward migration of the giant planets is a brief phase of rapid and enhanced scattering of the planetesimals, many of which would have been sent into the inner parts of the solar system, resulting in a temporary increase in bodies impacting the Earth and Moon in a period dubbed the Late Heavy Bombardment. Evidence for such a period of enhanced impact activity can be found by counting and dating craters on the lunar surface. The Grand Tack model instead describes an earlier phase, when the cores of the giant planets were still surrounded by a dense gaseous nebula, and the terrestrial planets had not yet formed. Hydrodynamical simulations show that a solitary Jupiter-mass planet, embedded in a disk, will migrate inwards due to the interactions with the surrounding gas. Left alone, Jupiter would likely have ploughed through the inner solar system, disrupting the formation of the inner rocky planets. The Grand Tack model argues that it was actually Saturn that prevented this from happening. Forming slightly later and further out, Saturn also migrated inwards, slowly catching up with Jupiter. The two planets eventually became locked in an orbital resonance, close to where the current orbit of Mars is located, which caused them to reverse course and move outwards together. At their closest, Jupiter and Saturn's orbit were likely less than 0.5 AU apart. This is about the distance between the current orbits of the Earth and Mars, and 10 times closer than today's separation between Jupiter and Saturn's. This Grand Tack manoeuvre played a big role in shaping the inner solar system, and is thought to be responsible for the relatively small mass of Mars, and for aiding the delivery of water-rich asteroids to the forming Earth. Together, the NEAS and the Grand Tack models paint a highly dynamic picture of the early solar system, and one in which Jupiter and Saturn had a profound influence on the evolution of the terrestrial planets. Other planetary systems form through similar processes, but small changes to the initial conditions can lead to very different outcomes and configurations. To illustrate this, we can compare the architectures of exoplanetary systems, planetary systems around other stars, to that of our own. This plot shows the masses and orbital periods of the solar system planets in green, and adds all exoplanets discovered since the early 90s, coloured by detection method. It is clear that many exoplanets are quite different from the ones in the solar system. In particular, astronomers were surprised to discover several new classes of planets, the aptly named hot Jupiters in the top left, and the so-called super-Earths. It is interesting to think about how the inner solar system could have looked without Saturn's last-minute intervention, or if Jupiter and Saturn would never have formed in the first place. Would we have had our own bloated hot Jupiter planet where Mercury is now? Would the formation of Earth have been prevented, or would she have continued to gain mass to become a super-Earth? These are questions that many astrophysicists are working hard to answer. Thanks for watching, and be sure to check out JupiterSaturn2020.org for tips on how to watch the Great Conjunction yourself, and for more information about the live events that the Astrophysics Group at the University of Exeter is planning.